All right, our next topic is L'Hopital's rule. So in these problems here, we want to find out if the rule applies, and then we want to apply it if it does. So first, to find out if it applies, we need to find out if the limit is going to 0 over 0 or plus minus infinity or over plus minus infinity. Positive or negative is the idea there. And so think about this here. When we plug in 2, we get 2 squared is 4. That's 0 on the bottom. Plug in 2, we get 1 minus 1, which is 0. So this is going to 0 over 0. So L'Hopital's rule applies. All right. And so let's go ahead and take the derivative of the top and the bottom. So we have the limit as x goes to 2. And we've got to take the derivative of the top. Well, the derivative of the top is a chain rule. So that gives us 1. The derivative of the inside is 1 times e to the x minus 2. And then this 1 goes away. Derivative of the bottom is 2x. And the 4 goes away. Does this... Now, let's plug in 2. When we plug in 2, oh, we get something out of this. Plug in 2, we get e to the 0 on top. E to the 0 is 1. I'll go ahead and write e to the 0 over 2 times 2. So this is 1 over 4. So the limit is 1/4. All right, how about this one? As we go to infinity, we have infinity squared plus 2 times infinity. That's going to infinity. And on the bottom, it's also going to infinity. So it's going to positive infinity over infinity, which means L'Hopital's rule applies. So let's take the derivative of the top and the bottom. So the derivative of the top is 2x plus 2. Derivative of the bottom is e to the x. Well, what happens as we go to infinity again? Well, this is still going to infinity over infinity. So we've got to take the derivative again. We can use the L'Hopital's rule again. Take the derivative of the top, we get 2. Derivative of the bottom, we get e to the x. Now, as x is going to infinity, this blows up, and we have 2 over a million, billion, trillion. All right, 2 over infinity, kind of. And so that becomes 0. That fraction is worthless. Okay, and there you have it. All right. Well, how about this? So we want to make a graph. And we want to make a graph with these characteristics. It needs to be continuous. We want f of 0 and f of 3 to be 0. And then we want to have these features here, okay? So the first derivative is positive, which means increasing, less than 1. It's increasing between 1 and 2. It's decreasing between 2 and 3. And it's decreasing after 3. The second derivative, which is our concavity, means that this is concave down, concave up, concave down, and concave up. So now we can make a graph here. So we're going to go from 0 to 1 to 2 to 3 and beyond. All right. So we know f of 0. So this is a graph of f. So f of 0 is 0. And f of 3 is 0. Okay? Now, let's think about this for a second here. Minimums and maximums. Okay? So right here at 1, we have it's not changing. So this is not a min or a max. The increasing and decreasing is not changing. At 2, the derivative is 0. And it is changing here. So 2 is a max. We do notice going back here, the concavity changes here. So this is an inflection point. Okay. 3 here, we have the fact that it doesn't exist. Okay, so it doesn't exist, so that means we can have an asymptote or a point. Maybe it's pointy. All right. And then the concavity is not changing there. So it's not necessarily going to be pointy, but it could be. Okay. Let's find out. Let's go and graph it. All right. So for the first area here, we're increasing in concave up. going to some point. We don't know how high. It doesn't matter. Okay. Then from, I'm sorry, that's concave down. Increasing concave down. Now we're increasing concave up. So we're going to go increasing concave up. Then from 2 to 3, we're decreasing concave down. All right. Now we actually have a little conflict here, a little bit of problem. All right. Is this possible to have a derivative here with concave up and increasing? It's actually not. So we run into a problem here. See, if we're going to go concave, we're going to decreasing concave down, well, that's got to go something like this. And once we do that, this is pointy. Okay, so we're going to go down to 0 there. Okay, so decreasing concave down, we have to go something like that. Okay, so we run into a problem there. So actually, this would have to be does not exist. Okay, and if that doesn't exist, this one doesn't exist. All right, so we got a problem there, and that's a problem with the problem. This one down here, okay, well, if that doesn't exist, the only way for this to really work is for this to be, well, it's not an asymptote, but it's going to have to be broken. Okay, so if this doesn't exist, all right, it's going to have to be a break. We know that f of 3 is 0. That's given to us. And so we got a break, and we're decreasing concave up. Okay, something like that. All right, so this is a problem here. These would have to be does not exist. Okay, so that's a problem with the problem there. All right, so there we go. Okay, and last but not least, we have, we're going to make a table here. Let's think about this. We want to make a table so that this is true. The change in f is greater than 0. So that means it's increasing. And it's increasing, but the rate of change that it's increasing is getting smaller. Okay, so this is concave down. If you want to think of a graph, concave down. So what's going on there is it's increasing, but it's concave down. So it's going up, 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 but it's starting to go up a little slower. So if this value is 1, it doesn't really matter. You can pick any number. You can pick 0, whatever. Okay, we're increasing, so it jumps up. Okay, so there's a difference of like 4. And then it's going to continue to jump up, but maybe it's jumping up a little less. Okay, all right, and then it's jumping up, so it's still increasing. Maybe it's jumping up to 8. Okay, so it's increasing, but the rate of change of the first derivative is decreasing. Okay, so it's increasing, but it's increasing a little bit slower as we move on. All right, that's the idea. Okay, all right, well, we'll leave it at that. Hope that helps. Again, sorry about this problem falling apart, but it is good to think about the fact that what was there was not possible. So there are combinations that won't be possible. Now, all right, you won't see a problem like that on the test. It'll work on the test. But that's what happens when we have a point. We have to have a point there because of this combination. And so that's where the derivative doesn't exist. All right? All right, thanks a lot.